Hello everybody,
Welcome to our Living Lab lecture series of ScaDS.AI.
and today we will talk about FloodVis that describes the visualization of flood ensembles.
My name is Verena Maleska from the Leibniz Institute of Ecological, Urban and Regional Development.
And I'm Marzan Tasnim from Computer Graphics and Visualization Chair of TU Dresden. And we will start with Verena Maleska, who will describe the data that we have used for our visualization.
Let's go ahead.
FloodVis, visualization of Climate Ensemble Flood Projections in virtual reality. Flood events are ubiquitous, and hardly a day goes by without a flood occurring somewhere in the world. Climate change causes a shift in the worldwide weather conditions. With the rising temperatures, extreme weather events will become more serious and flood events occur more frequently and intensely for several regions in the future. Researchers are working on the projections of possible future flood risk under climate change conditions to derive adaptive risk reduction measures. And they are using big data applications and AI methods to investigate the complex relationships between climate change and future flood risks. Besides mitigating climate change, common measures to reduce flood risks are existing, and flood simulations are crucial for risk reduction. Flood simulations are not always used to their full potential, since the resulting risk curves with their uncertainty bands are difficult to understand for decision makers and the people that are affected by flood risks. And therefore, we developed FloodVis for the visualization of ensemble flood events and their impacts in virtual reality. In general, flood risks are assessed by hydrologic and hydrodynamic design events that were derived from observations of the past. After a flood event occurred, we observed that there's a high discrepancy between the assessed risk and the real discharge conditions and damages. And this shows us that the risks are very dynamic and connected to a lot of uncertainties. Climate change has already altered the European flood risks and is expected to change this or to vary this in the future as well. And this means flood risks of the past are no accurate predictor for the flood risk of the future. And to consider this, we created an ensemble-based model chain that gave us the results for flood risk. And this comprehensive model chain includes 4 different modules: climate data ensembles, hydrologic modeling, hydrodynamic modeling, and damage simulation. And in the end, we are able to derive final risk curves, as you can see here. The module Climate Ensembles contains variables as temperature and precipitation for long time series, and they are used as input for the hydrological model to generate future flood events as its discharge curve. And these discharge curves then serve as input for the hydrodynamic modeling module to derive water depth in the inundation areas. And finally, the water depth are used to estimate the monetary damage for single buildings. The result of the hydrologic modeling part can be seen here on the left. This shows us a discharge curve for the flood event of 2002, for example, and the related precipitation. So we can see how the discharge develops over time at a certain point in our river reach. And many of those flood curves are derived for the future, and different inundation maps with several probabilities are then generated. And this you can see here. So we have different inundation maps for different return periods describing our probability. The technological implementation of the data that we needed to provide results for FloodVis can be seen here. So the 4 modules are connected to a database with climate data, of course, but also spatial data like a digital elevation model, land cover data, or soil maps. And we had to integrate additional information like high water marks or other information about the damages, for example. A lot of different software tools were applied, mainly R, Slurm, and GIS, to finally obtain the results of the flood risk assessment. And of course, high performance computing was necessary to run the different applications and also to deal with the different data that had a completely different structure in spatial resolution and temporal resolution. And to deal with those big data amounts, we have also had to use high performance computing. And now Tasnim will give you some information about the visualization procedure.
To visualize the flood data generated from the climate model chain, we have used digital elevation model with a resolution of 1 pixel per meter square, aerial images with the resolution of 1 pixel per 0.2 meter square, which were captured between 2018 to 2020. The building data describing footprint and height and the rooftop, we have used the level 1 data for that. All these geospatial datasets are published as tiles with the dimension of 2x 2 kilometers. We also have simulation and time series data with the resolution of 1 pixel per 4 meter square, which is a very high resolution. And for visualizing the time series data, we have a time interval for 1 hour. To create a 3D model with the supplied data, we have used some open source softwares like QGIS, CTGML Tool, Blender, and Photoshop. The digital elevation model of the study area is supplied in 9 tiles covering the entire area. Accordingly, the 9 tiles of the XYZ file format are merged using QGIS and cropped to the extent of the study area. The resulting DEM is saved into a new ASCII file, which is later rendered as a grayscale TIFF file. And the last step is to scale the resulting TIFF file to a square format using the software Adobe Photoshop and to export it to a 16-bit grayscale raw file, because Unity only accepts this as height map for the terrain. To create meshes from the simulation results, the Geographic Information Tool QGIS is used to fill the cells that do not contain water height values with the values of the cells next to it. This is done to remove the artifacts along the edges of the water surface in the visualization. This is the image of the artifacts that are caused by the lower resolution of the simulation data, and this image represents the removed artifacts along the shoreline. After the filling and transformation process, the meshes are created using add-on Blender GIS, and all the meshes are exported into one FBX file. The tiles of the aerial images are merged into a single file and cropped to the study area's extent, as already explained for the DEM. The resulting TIFF file is then downsampled using Adobe Photoshop to reduce the file size of 10 gigabytes. The information about the building data in the study area is accessible using as CTGML file. To convert the building data into 3D meshes, the Blender add-on up3date has been used, which only allows exporting CTJSON file, and finally all the files are imported to the Unity. After importing to Unity, the XR Interaction Toolkit is used to develop the 3D model, the terrain layer, the water surface, the teleportation area, as well as the skybox. The terrain layer is generated using the previously created height map in form of 16-bit grayscale raw file. The aerial images are then applied as textures. For the proper dimension of the terrain layer, the width, depth, and the heights are set to match the values shown in QGIS using the Unity editor. As for terrain height, the difference between the highest and lowest point of the elevation model is used. For the water surface, a plane is chosen. The scale of the plane is set to the extent of the simulation data. By switching the meshes on the planes, the different flood events can be visualized. To make the water surface look like realistic, a basic water shader from the Unity Asset Store is applied to the plane. To allow teleportation on the terrain and the water surface, the teleportation area component from the SteamVR has been applied for each of the game objects. For navigation and interaction, we have used HTC Vive headset and controllers, and here are the controller mapping. Now let's see some results. This image represents a 3D model of a community in Saxony, which has not been completely flooded yet. This is the completely flooded view of that specific area, but from a different view perspective. This image was captured from the 10 meters above the ground, and this image was captured from the ground itself. So this represents different perspective of the 3D model of that specific area. Here we can see some different user interaction from this image. It represents the menu selection. Here it represents the different datasets that are available for visualization. This help function guides the user with the interaction. The levels in the images are indicating elevation and water level from different distance and viewpoint, and this image represents scenarios together including uncertainty. The diagram shows water depth of 25 different events with low uncertainty for different datasets, and also the current scenario is attached to the left controller. Now let's have a demonstration. So this how a user feels when he enters to the virtual scenario, and user can have understanding of different water levels of different scenarios from the bar chart itself. User can also save the specific selection. Teleportation to the ground is enabled to avoid motion sickness, because in VR it is more likely to have a motion sickness when user moves inside the scene for a long time. User can identify the houses that are completely or partially underwater. This house is partially underwater and the other houses were underwater, more underwater comparing to this one. For the dataset selection, user can have different kind of simulation data as well as the time series data, and have a playback of the flood propagation over time. It is also possible to change different scenarios manually and increase and decrease elevation. So it is also possible to place the elevation levels. That includes the elevation and water height. Previously there was no water height. Still there is no water height because there is no water present at this moment. Yeah, another important thing, it is possible to point less critical area like this. Comparing this area is less critical comparing to that area. And snap turn is another feature that has been enabled to avoid motion sickness. So it user can turn their head 45-degree angles without moving their head, and this is the help function for the users. And it is also possible to change the playback of the flood propagation. Now Verena will talk about the future work of this project.
Now you got an impression how FloodVis looks like, and you are maybe wondering what we will do in the future to develop the tool more. So our first plan is to include a guided map and a guided tour to lead the people that are trying to get in touch with FloodVis more by orientation. We also want to visualize damages for single buildings so that it is possible to go into the building and see, depending on different stages, how much damage the flood causes. And for the future, we are planning to extend FloodVis to other extreme weather events that might be changed by climate change. For example, drought events, heat waves, or extreme precipitation.
Thank you so much for joining with us today.
We hope you enjoyed our Living Lab lecture today.
If you are interested, feel free to get in touch with us.
Thank you.